This video is going to provide a reminder of a concept called vector projections, and we'll also talk briefly about collinearity. But first of all, vector projections, and I guess to start with, we've got a couple of formulas on our formula sheet for this, so let's have a look at those. There they are, the vector projection of vector A on vector B, and we're given two different formulas there, one relating to an angle and one simply relating to vectors which I guess we'd normally expect to be in component form. So let's have a think about what the vector projection means and then how it is that we end up with these formulas. So, excuse me, when we think about vector projections, another way we can talk about them is vector resolutes, or the idea of resolving a vector in certain directions. So let me give you an example here. Let's say we've got vector B there, another vector A here. And the question I would ask myself to consider what a vector projection is would be to say, can I resolve vector A into the sum of two vector components, one of which is parallel to B and one of which is perpendicular to B? So let me grab another color. Let's draw a vector here which is perpendicular. See if we can get that. That looks roughly perpendicular there. So there's a vector perpendicular to B. The vector that's parallel to B would be that one there. So I'm expressing vector A as the sum of, let's call this one here U, that one there V. I'm saying A can be written as the sum of vector U plus vector V. Now vector U, which is in the direction of B, or we could say on B, vector U is in fact this thing here, the vector projection of A on B. So this vector U, this one shown here, is the vector projection of A on B, or in the direction of B. So let's just record that here. U is the vector projection of A on B. Before we go any further, it's worth just realizing or recognizing that there are other ways of describing this. So vector projection, some texts or some places you'll see it written as the vector resolute, because of that idea we just talked about of resolving a vector in other directions. So the vector resolute of A on B. And likewise with the word on, we might see it written as in the direction of, or even parallel to. So the vector projection of A in the direction of B, or the vector resolute of A in the direction of B, all of those have the same meaning. Now, our formula sheet doesn't give us any formulas for V, but that vector V could also be described as the vector projection of A perpendicular to B, or the vector resolute of A perpendicular to B, because that's the one there. Alright, so how is it that we get then to those formulas there? Well, let's write an angle in between them, and then let's note that using trigonometry I could say that cos theta is equal to adjacent, which would be just the magnitude of U, divided by the hypotenuse, wouldn't it? So cos theta is equal to, let's just move that up a little bit there, cos theta is equal to adjacent over hypotenuse. I think that's what I said. Adjacent over hypotenuse is certainly right. So magnitude of U over magnitude of A. And so therefore we could rearrange that and say, well, the magnitude of U is therefore equal to magnitude of A times cos theta, isn't it? So that would be an expression for the magnitude of U. If I wanted then an expression for the vector U, I'd need a directional component. So I could do that simply by saying, well, there's the magnitude, and to get it in the direction of B, all I really need is unit vector B, isn't it? So if I have unit vector B, that's going to ensure that it's going in this correct direction, and the magnitude A cos theta is going to give it the right length component, the right sort of scale component there. So that's how we come up with that first one there. Expression for the vector projection, magnitude of A times the cosine of the angle between them times unit vector B. So how do we go from there to the next bit? Well, let's first write it down. So we could show in a few steps that a magnitude of A times cos B, this first bit here, can alternatively be written as just A dot product unit vector B. Now I'm not sure whether that's something that you could do, but maybe I'll sort of have a go at doing that in a couple of steps. It's worth, or in a couple of moments, it's worth also noting that we can write this in a third alternative way. So those two ways there are the ways that are expressed on the formula sheet. So I guess in that sense you don't have to remember them. The third way, if you're going to use it, you do unfortunately have to kind of remember it or remember how we get it. And the reason for this one is that it looks a bit more complex, but it's actually probably a little bit easier to use. So again, with a couple of steps of working out when we understand the dot product, we could show that those two expressions there are equal. Alright, so all of those are expressions for the vector projection of A on B. 2 out of the 3 of them are given on the formula sheet. So we should note that when we're getting that vector projection, we are getting a vector as our answer. Okay, so we're using a dot product in there, particularly if we're using the second or third form there, we're using a dot product, but we're getting a vector because it's got a directional component as well. Right, let me do an example, I think. So in exercise 4E, and let's go to question 4. I'm going to do part B. So this says, for each pair of vectors, find the vector resolute of A in the direction of B. So textbooks using the language of resolute, but vector resolute of A in the direction of B is the same as the vector projection of A on B. So our two vectors that were given in this particular question here are vector A, which is I minus 3k. So you might recall back in Unit 1 we did this with these with two-dimensional vectors, so now we can extend to three-dimensional vectors. So B is I minus 4j plus k, and we want to get the vector projection of A on B. Of A on B is going to be equal to, now I'm going to use this form here because I suggested that was the easiest one to work with. So A is 1, 0, negative 3, isn't it? And B is 1, negative 4, 1. And so then we're going to take the dot product of 1, negative 4, 1 with itself, 1, negative 4, 1. And then the vector component is 1, negative 4, 1 there. Alright, so what do we do when we get those dot products? 1 times 1 is 1, plus 0 minus 3, so 1 minus 3 is negative 2, and the denominator is going to be 1 plus 16 plus 1, which I think is 18, and then we've got the vector b. So if I was to write that in ijk form, that would be negative 1/9 times I minus 4j plus k. So it's pretty clear from the way that that's written that this is in the direction of b, isn't it? Because there is vector b. It's just a scaled version of vector b, which is exactly what the vector projection is. Because it's in the direction of b, it's just going to be a scalar multiple of vector b. So I think that form is kind of the easiest to use, because remember, if we use unit vectors, we've got to find magnitudes, and we'll have square roots in there. Now, we'll be multiplying the magnitude by itself because it's in both of these here, so the square roots end up disappearing, but it's just that if we use this form, we don't sort of have to go through that process. However, there is a reason that these two forms here are useful, because the unit vector b here is the bit giving the direction of vector b, so it's giving the direction of the vector projection, but it only has a magnitude of 1. So therefore, this bit here, magnitude of a times cos theta, or a dot unit vector b, that is actually giving the sort of scale component here. So if you like, it's giving the magnitude of vector u, although it could be negative, so we shouldn't technically say magnitude. It's kind of the signed length, so it could be positive or negative, but it's kind of saying how much is in that direction. And so for that reason, we sometimes call that bit the scalar resolute. So note that a dot unit vector b is the scalar resolute, or projection of A on B. Alright, you could also find V. You've got no formula for V, for the vector component or vector projection of A perpendicular to B, but we could of course just say, well, if A equals U plus V, then V is going to be A minus U. So once we've found this vector here, if I subtracted that from vector A, I would have vector V. That's just a simple arrangement of that. Alright, second thing I said would just quickly touch on in this video would be the idea of collinearity. So we need two L's there, collinearity. What is collinearity? Well, points are collinear when they lie on the same straight line. So if I have 3 points here, something like that, they are collinear if they lie on the same line. So let's just quickly consider the result that we need for this. So for A, B, and C to be collinear, well, if they are collinear, then it's going to follow that the vector AB is going to be a scalar multiple of vector AC. Okay, where k is any real number, non-zero of course. So maybe we should just include that there, accepting the value 0. I need to just neaten that up a little bit so it actually looks like a B. So AB is equal to k times AC. In other words, vector from A to B is a scalar multiple of vector from A to C. And you might say, well, isn't that exactly the same rule as just for parallel vectors? And yes, it is. But the thing about this is, because they're parallel and they share a point, a common point A, if this vector and this vector are parallel and they share a point, well, then it ends up that those 3 points have to lie on the same line. And so the last thing is to say that this is implied in both directions, that if we can show, and this is probably where the result's a bit more useful, if we can show that AB is equal to a scalar multiple of AC, or AC is a scalar multiple of AB, that is sufficient to show that A, B, and C are collinear points.